Okay, now we're heading to an even bigger result that will get us even closer to this idea of modular arithmetic that I keep referring to. We're going to use the math that we did in class in that Euclidean algorithm introduction activity, and we're going to apply that technique we talked about to be able to write two integers as a linear combination of their GCD. So for right now, we're just going to state it as a fact. The proof we'll put off to later. So the theorem, what we're going to use now is for any non-zero integers a and b, there exist integers s and t such that the GCD of a and b is equal to as plus bt. So whenever you write something of this form, we call it a linear combination. I prefer to make it more specific to say linear combination with integer coefficients. Because especially for those of you who've taken Math 10, it's really important to say what types of coefficients you're allowing yourself to use. As we mentioned when we started Chapter 5, we're trying to keep ourselves completely in the world of integers. All right, so we have our first fact. Now, second fact. Every linear combination of a and b ends up being a multiple of the GCD of a and b. Next fact that follows directly from that is the greatest common divisor of two non-zero integers a and b is actually the smallest positive integer among all their linear combinations. So just to kind of play around with this for a moment, if I have 8 and 12, the possible integer linear combinations of this, well, there's infinitely many linear combinations. I could write 2 times 8 plus 3 times 12. That will end up with a big number. I could do negative 3 times 8 plus 4 times 12. I could do negative 3 times 8 plus 2 times 12. I could do 7 times 8 plus negative 6 times 12. So there's infinitely many linear combinations I can make out of 8 and 12. What this theorem is saying is if I take all the possible linear combinations of two non-zero integers, for example 8 and 12, the smallest positive integer among all the answers of these calculations, if I were to do these calculations, the smallest positive answer would actually be equal to the GCD. Okay, so let's think about that. The GCD of 8 and 12, just kind of by inspection, is 4. Can we just think off the top of our head of a way to write 4 as a linear combination, an integer linear combination of 8 and 12? Well, for this one, it's kind of straightforward. If I do negative 1 times 8 plus 1 times 12, I'm going to get 4. This here is an example of a linear combination of 8 and 12. If you were to calculate the answers to all of these, either the answers would be negative or 0, or there would be some positive number bigger than 4. You can feel free to pause the video, try other linear combinations, play around with it, see how that goes. Okay? But the point is that we have to combine these three results to be able to use them towards something else. Anytime we create a linear combination of two non-zero integers, that answer is going to be a multiple of the GCD. We want to know the exact choice of coefficients, the exact S and T that will give us the actual GCD and not a multiple of it. So we're going to work our way gradually to what we need to use that. Let's look at this example for now. If n and n plus 1 are two consecutive positive integers, we notice that we can write n times -1 plus n plus 1 times 1, and when we simplify this, we're going to get 1. 1 is the smallest positive integer that exists, period. And we know that every linear combination of n and n plus 1 will be equal to a multiple of the GCD of n and n plus 1. So that's saying that 1 is a multiple of the GCD of n and n plus 1. In other words, it's saying that the GCD of n and n plus 1 divides 1. If a number divides 1, it has to either be 1 or -1. But we know the GCD is positive. So that means the GCD has to be 1. And that tells us that the GCD of any two positive consecutive integers is going to be 1 for any pair of consecutive integers. Before we continue exploring linear combinations of integers, we're going to look at one quick definition, which says two integers a and b are relatively prime if their GCD is equal to 1. Another way to say that is their only common divisors are plus or minus 1. Notice that in the last example, we have a pair of integers that are relatively prime because their GCD is equal to 1.